So today we're going to speak about basic concepts. What's the basic definitions that we're going to explain today? The thermal resistance and thermal transmittance. Well, if you read that definition, it's R, the thermal resistance. R is defined as the ratio of the temperature difference between the two phases of a material to the rate of heat flow per unit area. Well, what does it mean? Well, the thermal resistance is it's a property of a material. We are talking about solid materials here. So it's thermal resistance. So it's difficult if heat has to go through a material using the mechanism of conduction. It can be easy or it can be difficult. Okay, so the thermal resistance measures the difficulty that the heat has to go through a material. Thermal resistance. A material is resistant to conduct heat or thermal heat energy in and you can understand that if we have a very thin paper, it's very easy for the heat to go through the paper. But if we have a huge or a very thick material, it's very difficult to go through it. Well, so it has to do with the thickness of the wall. And if you look at the wall here, we have different thicknesses. We have the wall itself. So it's how much is this? Maybe a foot or 1 foot and a half. And then we have a glass. So the glass is much thinner than this. The glass is transparent and this is opaque. But there's a question of thickness. So we can understand that the heat goes easily through the glass than through the opaque wall. It makes sense. But thickness is not everything that counts. There's another property that we will be studying. Okay, but it's something the heat has to go through the materials, through the wall, through the roof, through the floor. We have heat here. The temperature here today probably is higher than the temperature outdoors. So the heat tries to go outside and it has to go through the walls. Is it easy or is it difficult? Well, the magnitude that measures this is the thermal resistance. It's a ratio between all that. Okay, this is the definition, but you have to understand the concept. So we need to increase the thermal resistance of materials because we have to prevent heat from leaving this room if we are in winter, or we have to prevent heat from entering the room if we are in summer. Okay, so first, do we need a lot of thermal resistance or very low thermal resistance? A very high thermal resistance is better in buildings, period. There is no debate or question about it. We have to increase the thermal resistance of walls, roofs, and floors. Another concept, the thermal transmittance, defines the ability of an element to transmit heat under steady state conditions. Well, the relationship between thermal resistance and thermal transmittance is very easy. The thermal transmittance is 1 divided by R. Okay, so if we have a high thermal resistance and we have a very low thermal transmittance. That's it. So if we understand one of the concepts, we understand the other one. Very high thermal resistance means very low thermal transmittance. Usually we have we have these two properties. So when we are reading specifications of materials, when we are talking about walls, we will, if you read articles or websites, you will read about the R value. If you are talking about windows, then we will talk about the U value. Okay. But it doesn't matter because it's the same. If we need a very high R value, that means that we have a very low U value. So what is the best material? The one with the highest R value, the one with the lowest U value. And this is important, the steady state conditions. Everything that I'm telling you is not true, okay? It's close to the truth, but it's not 100% accurate. But we get by. We are architects, we're not physicists, we're not trying to put a man in a rocket and fly to Mars. We're just designing buildings. So to design a building, steady state conditions are enough. But this is not what happens. Steady state is that we have a temperature indoors, we have another temperature outdoors, and we assume that those temperatures are not changing. It's not true. Temperature changes. It changes inside, but we have systems to prevent this temperature to change a lot. We have a range between 70 and 75 Fahrenheit, which is comfort temperature, but the temperature outdoors changes a lot and we can't control. In winter, we have 0 Fahrenheit. In summer, we have 95. Okay, so the temperature changes. Everything that we're going to study in this course, it's under steady state conditions. That's fine. In one day, if we look at throughout the year, the temperature changes a lot. If we look at one day, it doesn't change that much. In winter, it's always cold. In summer, it's always warm. Okay, but all the formulas that we are studying only work if we assume these steady state conditions. And this is something that you need to understand when it comes to formulas. And we rely on formulas. Oh, no, there's a formula. What's done? That's the result, and that's it. Well, formulas are simplification of reality. We have to simplify reality because reality is too complicated. And so if we try to understand what's going on, we need a formula, and the formula explains part of this reality, but not everything. Okay, so don't fight. No, my teacher told me that this is the formula and it should be right. Under the steady state conditions, the formulas are right. But someone can tell you, okay, what if the outdoor temperature changes? What if we have something inside the room that makes indoor temperature change? Then this formula doesn't work. Okay, so keep that in mind. What's next? This concept, the thermal conductivity. It's related to the thermal resistance. How can we relate thermal resistance and thermal conductivity? The thermal resistance, it's a concept that we apply thermal resistance to construction elements. And what is a construction element? A wall or roof. The thermal conductivity, it's something that affects the material itself. It affects brick or gypsum board or concrete or steel or whatever. Okay, so we have materials, and a material has a thermal conductivity. Then if we put together different materials, and building walls means that we have different layers of different materials. If we put everything together, then we can calculate the thermal resistance of that wall. Okay, so we have two different things: thermal conductivity for a material itself, thermal resistance for different layers of different materials. So what is thermal conductivity? It's a measure of the ability of a material to allow the flow of heat from its warmer surface to the colder surface. So it's the ability of a material to allow the flow of heat, or to allow the heat flow. That's the thermal conductivity. I'm sure that here we can see, or we can understand thermal conductivity very easily. So we have a table. So you all have a table. Can you please touch first the board, and second the leg? And can you tell me what part of the table is colder? The leg is colder. Do you all agree? Someone thinks that the board is colder. Okay, so we feel that you are wrong, by the way, but we all agree because we are all human beings. Okay, so the temperature is the same. So the temperature of the board and the temperature of the leg is the same. So the leg is not colder. But when we touch the leg, what do we feel? We feel that we are losing heat. What's our body temperature, by the way?
38.6.
98.6. Okay. Fahrenheit. And what's the temperature of the table?
Probably in the 70 to 75 range.
75. Yes. So the temperature of the table should be the temperature of the room. So what's the temperature of the room? Here we have 76. It's 76. Okay, so the table should be at 75, 76. In our valley, it's at 98 point something. So that means that when we touch something, we feel that the temperature of this, the chair, the table, whatever, is colder than our hand. And that's true. But the temperature of the board and the temperature of the leg should be the same. Everything in this room is at the same temperature. This board, the wall, the glass, the handling. Okay, so everything's at the same temperature, the higher temperature. Everything should be at the same temperature, around 75, 76 Fahrenheit. What's the difference? That if we put two objects at a different temperature, so we have an object, we are the object, and the temperature is around 98 Fahrenheit, and then we have another object that is at 75 Fahrenheit. Okay. So if we have a high lambda is the value of the thermal conductivity, lambda or K. You will find different formulas or different books. We can have K or lambda. Anyway, it's a thermal conductivity. So if we have very high thermal conductivity, we can feel that there's a lot of heat going from this object at 98 Fahrenheit to this one. So if we have exactly the same objects at the same temperature, 75 and 98, but this is a very low thermal conductivity. Then what we feel is that the rate at which we are moving the heat is very low. Okay, so this is what I feel as cold, and I feel this as not as cold. It's not the temperature of the object, it's the rate at which I'm losing heat, and that property is the thermal conductivity. Okay, so if I touch something and it seems cold, that means that I'm losing a lot of heat. And it doesn't seem as cold, it means that I'm not losing that heat at that rate. Okay, so it's about the rate at which I lose my heat. Of course, there might be a difference. If I have something that is at a different temperature, I will feel that I'm losing more heat. Okay, so I can lose heat because of two things, because of the temperature difference or because of the thermal conductivity. If the temperature of both objects is the same, then I only feel the thermal conductivity. If the thermal conductivity of two objects is the same, then it depends on the temperature. And if I have different temperature and different thermal conductivity, then both factors take place, okay? But there's nothing that makes me think that the temperature of the leg is lower than the temperature of the board, because it's in the same room. We don't have a heat source close to the board, or we don't have a heat source close to the leg, so probably the temperature is the same. But we feel that we are losing heat, and this losing heat means that the thermal conductivity of the leg is different than the thermal conductivity of the board. What is this? If we have a high thermal conductivity, we have a conductive material. And if I have a low thermal conductivity, we have an insulating material. Okay. So we need thermal insulators in our walls. We need thermal insulating materials. We need materials with very low thermal conductivity. But then, well, okay, this is the thermal conductivity. Units are very important. The units of thermal conductivity are this. We have a watt, which is power, divided by Kelvin or meters. This is temperature, and this is meter distance. Or we have a BTU hour, it's the power, and then divided by Fahrenheit and feet. Okay, so these are international units. These are imperial units, but it's always power divided by temperature divided by distance. So these are the units of thermal conductivity, and it can be either K or lambda. Okay, the formulas. There's something that relates thermal conductivity and thermal resistance. So this is the thermal resistance as R, so equals thermal conductivity. No, it's the other way around. It's so this is wrong. I changed it. It's the thickness or the distance divided by the thermal conductivity. Okay, so that's the formula of the thermal resistance. So thermal resistance R equals W. This can be D, E, W. Its distance divided by thermal conductivity. This can be lambda or K. Sometimes you will find R. So it depends on the book, and depends on the edition. You might find but units are important, and units are the power, and the units of thermal conductivity is power divided by temperature and distance. And then we can have watts, BTU hours, we can have Fahrenheit or Kelvin or Celsius, and we can have whatever, but it's always that way. So the thermal resistance, if we do have the thermal resistance, here we have W, it's a distance. Okay, so this is the distance divided by power divided by this. So the unit of thermal resistance is temperature times distance to the power of 2, because we have two distances here. We have distance and distance here, divided by power. Those are the units of thermal resistance. The units of thermal conductivity is power divided by temperature and distance. We have distance here, we move this up, and we have temperature, distance, to square to the power of 2, divided by power. Okay. So those are the units. What are the units of thermal transmittance? We have to move this, so it's power divided by temperature times this to the power 2. That's it. We have to get used to working with units, because if we make a mistake, the only way to understand that we have made a mistake is working understanding the units. So we have distance, we have temperature, we have power, and then so these three concepts are difficult to understand because we always have the same units. Here we have power, temperature, distance. Here we have temperature, distance, power. Here we have again the power, temperature, and distance. But anyway, we have to become familiar with this. Not today, but over the next few weeks, you have to master this. And when you are dealing with thermal resistance, you need to know the unit. When you are dealing with thermal transmittance or thermal conductivity, it sounds the same, but it's different. And what do we have here? So this is the thickness. This is the distance that we are talking about, the thickness of the wall. We have the power. The power is the heat that wants to go through this wall. Okay, so we have this room at 76. Probably outside we have 60 or 62 or whatever. So the heat goes from the warm area to the cold area. So it has to go through the glass, it has to go through this. It's easier for the heat to go through the glass because it's thinner and probably the thermal resistance of the glass is less than the thermal resistance of that wall. But the heat goes through the wall. So it depends on the thickness. Usually, the thicker the wall, the more the thermal resistance. It makes sense. But it depends also on the thermal conductivity. So what's the challenge? The human being has tried to have a material with a very high thermal conductivity in a very low thickness, because designing or building thick walls is much more expensive than building thin walls. Makes sense. Okay. So what do we need? A thin material with a very high thermal conductivity. Do we have this? We do. And it is in this room. Here. Okay, so all this is thermal insulation. We don't see this in our walls. We don't see it. Why? Because, well, first, it's fragile. Okay, so we can scratch it. If we have a finish in our room, it has to be something like that, hard enough, because if we, yeah, we can damage easily. Okay, so we can damage the material easily. It's very light. It's not heavy at all. Very light. And probably this thickness of this thermal insulation has the same thermal resistance as 2 feet of brick. That's perfect. This is what we need. We need something light because moving this is very easy. Moving 2 feet of brick, you need a lot of people to do that. It's very light, it's very cheap, and it has a lot of thermal resistance. So we need a lot of this material inside the walls. So if we have this wall, what's the thickness of this wall? You can see the thickness of the wall. The first layer is brick. Probably we will have like 10 inches of brick, and the rest probably it will be thermal insulation. And then we have a finish. We have this finish. And this is gypsum board or plaster board. So this would be like 1/2 inch. We have 10 inches of brick, and the rest probably it will be thermal insulation like this. Okay, but those are thermal insulating materials, and they are completely different. So touching these materials, you can tell that they are completely different. This and this is the same material, but the manufacturing process is different. So that's why the aspect or the external, the color, and even the matter itself. Here you see that we have small cells. And here we don't have this. This is something different. Okay. It's the same material, it's the same polymer, polystyrene. And this is something completely different. It's wood fiber, or can be wood fiber or glass fiber. But these are this is the fiber, and this is the plastic. So they are two different materials, but all of them are thermal insulating materials. Okay, so this is what we need. We need to reduce the rate at which the thermal energy moves through the wall. Okay, so we're reducing the rate, not the amount but the rate at which this heat is going through the wall. We have a thickness. In modern architecture, we have to reduce the thickness as much as possible. Why? Because that's the main difference between contemporary architecture and the architecture that we had 2 or 3 centuries ago. At that time, they didn't have those materials. So if they wanted to create a good architecture, they had like 2 or 3 or 4 or 5 foot walls. So they increase the thermal resistance by increasing the thickness. Nowadays, we have to increase the thermal resistance by increasing or by decreasing the thermal conductivity. So thickness matters because in Manhattan, we cannot have 5 foot walls because we lose a lot of money. Okay, so what can we do? We have to use this kind of material. It's lighter, it's faster to build. You need fewer people to build walls like this than building walls made of stones or bricks. So it has a lot of advantages. So this is the first thing, reducing the rate at which we lose heat with thickness or with the thermal conductivity. So we know the thermal conductivity, and another thing that we can control is the temperature difference. We can decrease or reduce the rate at which we lose energy by decreasing the difference between indoor and outdoor temperature. But there's nothing we can do here because the indoor temperature has to be always between 70, 75, because this is comfort temperature. So yeah, if in winter, if we keep our buildings at 70, we lose less energy than keeping our buildings at 75. It makes sense. But outdoors, we can't do anything. If the temperature outdoors is 0 Fahrenheit, we can say, okay, let's raise the outdoor temperature. Well, we have the global warming, and apparently outdoor temperature is increasing. But in winter in New Hampshire, it doesn't happen yet. Okay, so all these things are connected. But the goal, if we understand the goal, we understand what we have to do, and the goal is to reduce the rate at which we lose heat. We can increase the thickness of the wall. We can decrease the thermal conductivity of the material, and we can decrease the temperature difference between indoors and outdoors. But what have we done over the last 100 years? Decreasing the thermal conductivity of materials. So those materials didn't exist a century ago or 100 years ago. Now we have it. We have those materials, and we use it. We use massively all these thermal insulation material. So we understand the concept. We have the formulas. The formula is quite easy. Okay, so we only have these 2 formulas. R equals thickness divided by thermal conductivity, and the thermal transmittance is 1 divided by R, the thermal resistance. So those are the 2 formulas that we have to understand today. What's next? Well, as I told you, we have different layers in walls. It's not just a material. You see that the outdoors we have brick, and indoors here we have this finish. We have this plasterboard, and in the middle there will be other materials. At least we need the thermal insulation. Okay, so at least we need 3 materials in a wall. At least we can have more. But we need the external finish. We need the internal finish. And here we have thermal insulation. Okay, at least we need these 3 materials. Something to protect the thermal insulation from outside. And what do we have outside? We have rain, snow, we have wind. Okay, so this external finish, it's very important because this is what protects our building from outdoors. And then what we have inside? Inside, we have people. Do we have to protect our building against people? Well, we do. But we have to protect people against outdoor conditions. And then this internal finish, yes, if there are someone trying to destroy the internal finish, well, destroy just by. Okay, so it has to be resistant, but it has to be pleasant. It has to be something beautiful. Well, beautiful, at least that we feel that, okay, it's good enough. So the internal finish, it's also important, but the external finish is more important to protect the building. Then we have the thermal insulation. We don't touch or we don't expose thermal insulation. We don't expose thermal insulation inside or outside. We can't do it. We have to protect it. So that's why we need 2 layers. And then we have the internal finish, which is the material that is in contact with the people inside. Okay. So this is what we have to understand. At least we have 3 layers. And then there are 2 more layers that we don't see, but they exist. We have the air. The internal air. And then we have the external air. Okay, so those are 2 layers, 2 invisible layers, but they are there. You see this dashed line? Well, there's some air in contact with the wall or the roof or the floor. And that's important because each layer has a thermal resistance. Okay, so we can have a thermal resistance of the material 1, we can have a thermal resistance of material 2, we can have thermal resistance of material 3, but we also have a thermal resistance of the air inside and thermal resistance of the air outside. And then what's the total thermal resistance of the wall? We have to add all these up. And then this is the total thermal resistance. So now it's quite easy. What's the thermal resistance of material 1? It's the thickness of material 1 divided by the thermal conductivity of material 1. What's the thermal resistance of material 2? The thickness of material 2 and thermal conductivity. Material 3, thickness divided by thermal conductivity. And then we have the thermal resistance of external air and the thermal resistance of internal air. So this is all you need to know. We have different layers. Each layer has a different thermal resistance. Each layer has a different thickness. So this is W1. This is W2 and W3, thermal conductivity 1, thermal conductivity 2, thermal conductivity 3. And then we have the 2 air layers. This is more difficult to understand because you don't see that. But there's something that adds a little thermal resistance to the wall due to the air inside and outside. So this is what we have here, okay? Here we have this drawing, and in this drawing, Q is this arrow. It has to go from, you see, temperature 1 is higher than temperature 2. So this could be indoors, and this could be outdoors if we are in winter. And the heat, this Q, this arrow, goes from temperature 1 to temperature 2 in this direction. We have a thermal conductivity here. It can be either K or lambda. We have different thickness, W here. And here we have X1, it's the width, but this is difficult to understand the air here and the air there. So it has a thickness as well, this air layer that we don't see, but it's there. And that's it. If we have more layers, then we have to add different thermal conductivities and different thicknesses to these. And that's it. Due to conduction, remember that we were talking about conduction, convection, and radiation. So due to conduction, that affects solid elements. The thermal resistance, it's distance divided by thermal conductivity. And distance can be d, w, and the thermal conductivity can be lambda or k. Okay, but it's always thermal resistance is distance divided by thermal conductivity. And then convection radiation, we have an extra thermal resistance, and we use this H value. And the thermal resistance is 1 divided by H, the external one, or the internal one. So this coefficient takes into account the heat transfer through convection and radiation, because we don't have a solid. The air that we have here is not a solid. So that's why we can calculate this thermal resistance like this. So there are tables, and they gave us these tables give us this H coefficient, external, internals. It's different if we are talking about walls, roofs, floors. Okay, but it's an H, and then we have to do this. We have to get the thermal resistance. We have to divide 1 divided by H, and then we can add everything up. So if we want to calculate the total thermal resistance, we need the external air layer, the solid layer, and then the internal air layer. And then we add everything up, and we end up having the total thermal resistance. So it's not difficult. It's just a formula. We need to know what thermal resistance is, and then we have to add everything up. If they are asking, or we have to give an R value, that's it. If we have to give a U value, then we have to divide 1 divided by R, and then we have the thermal transmittance for the U value. So it depends. In different codes or different regulations, we have to use R or we have to use U. But if you have calculated R, calculating U, it's a piece of cake. Okay, so this is what the multi-layer wall is. If we have different layers in walls, roofs, floors, okay, so we don't have just a single material. And even if we have a single material, we have to consider the internal air and the external air. So at least we have 5 layers now. Remember that we need the external finish, the exterior air, then we have the thermal insulation, the internal finish, and the internal air. So at least we have 5 things to add up. Okay, at least 5. Do we have examples here? Yeah, we do. And yeah. And I think 90% of houses in this country are made of this. So this is the most simple wall that we can have in especially in residential buildings. We don't have this in big commercial buildings, but what we have, the yellow stuff here is a thermal insulation, and then we have internal finish and external finish. In this case, the finishes are the same. What do you call this kind of board? Hmm?
1/4 inch plywood.
What material is this?
Plywood.
It's wood, it's plywood. Oh, we're getting closer. What's the difference between
One point.
plywood let's look at the image. This is not plywood, by the way, this is plywood. So is it the same? It's not. Do we have plywood?
Are you talking about like particle board?
Hmm?
We're talking about like particle board?
Particle board. Yeah, it can be particle board, but this is the oriented.
There's different types of plywood that you can buy.
Yeah,
for specific job.
but the technical, yeah, this is the OSB.
Yeah. that's
It can
what
be
we-
particle board.
That's what we can only use on job sites, the OSB.
Mhm.
Roots and walls and all that.
Okay, but anyway, this is the OSB and the other one is plywood. Is there a difference? Well, it's made of wood, but the way it is arranged, so here we have wood and there are different layers of wood, and then we stick with glue all these layers in different orientations, and we end up having this. Here we have particles, like these particles, and we use glue to put everything together. Okay, so it's wood and glue. And why do we have this? Because it's much more, it's cheaper doing this at working with the actual solid wood. Okay, so if you 200 years ago, they didn't have plywood, they didn't have this OSB, they had actual wood, but it was too expensive. And well, now you can manufacture this and it's quite cheap and quite reliable because the glue adds reliability to the material. Okay, but this is it. So a wall is something as simple as this: internal finish, external finish, and then something in the middle. Then we paint it, yeah, but the paint is so thin that doesn't affect the thermal resistance of the material. So that's the wall. Sometimes we have plywood, sometimes we have this OSB, and then you paint it because and sometimes you will see this kind of wood exposed because it's full. People like it. So let's continue. And this is the heat radiation convection coefficient. Adds a thermal resistance to the multi-layer wall. And this is what so the value of the H, it depends whether we have the indoor or outdoors or internal and external one. Okay, the values are different. And it's different depending on the heat flow. So when we have a horizontal heat flow, that means that this is a wall. Because if we have a wall, the heat flow goes in this direction. If we have a roof, the heat goes up. And if we have, well, the heat goes up in a roof. It depends if we're talking in winter or in summer. I'm assuming that we're always talking about winter. Okay, so if we are in winter, this is a roof and this is a floor. Because the temperature here is 70 and the temperature outdoors would be 0. So if we are here at 70 and here 0, the heat goes up. And if this is 70 and this is 0, the heat goes down. Okay. But if this were summer, it would be the other way around. In summer, if we have 100 here and 70 here, the heat goes down through the roof and goes up through the floor. Okay, so don't think about winter, summer. Think about or roofs or walls. Or well, if it's horizontal, it's always a wall. Okay, so even in winter and summer, it's always happens. So it will it's horizontal in walls, but in walls, in roofs and floors, it depends on where the highest temperature is. So if you are moving the heat upwards, then you need this value for HI and HE, the internal and the external. And if the heat flows downwards, then we have this value. Okay, so it's not Well, it's not that difficult because as you can see, the external value is always the same. It's always 2.93 BTU hour feet square Fahrenheit. Okay, so this value is always the same. We have two units here, international and imperial units. We are working with imperial units, so we need to, and you don't have to know these numbers by heart. If we have exams, you will have access to it's open book. It's always an open book exam, the final or the midterm, open book, open laptop. Okay, so you have access to this value, you don't have to learn them. And then the other value, it's 1.6, 1.96, 1.05. And this is interesting. We all know that the heat tends to go up. This is something that we learn when we are kids. Our parents say, the heat tends to go up, or our grandparents or our teacher in high school or whatever. And this is something that we take for granted. The heat tends to go up. It's not always like this, because if the temperature of the floor is lower than the temperature here, the heat flow goes down. Okay, but it tends to go up. If it tends to go up, this is it's like the ability to go. So it's higher than this one. Okay, so those values are different. So when the heat goes up, that means that it's easier, and this value is higher than this one. Okay, so that's if sometimes you don't know. Okay, if the highest value means that the heat flow goes up, the lowest value means that the heat flow goes down, and this is always something in the middle. The wall is something in the middle. But anyway, we need to understand this, and I think I told you that we can't see this layer. Sometimes we can. Okay, sometimes we saw this. If we are on a road and the road is dark, made of asphalt, and it's too hot and the sun is striking on this road. At the end of the road, we see that it feels like moving. Have you noticed that sometimes? What do you call this effect? What do you say? Oh, look at this. Look at
Heat waves,
what?
like heat waves above the
Heat
ground.
waves. Well, I don't know. Maybe that's there's not another expression, but in Spanish we have this espejismo, which it's a cool word. But anyway, yeah, heat waves. We can notice that if something is very hot, if the temperature difference between this and the air temperature is too high, we see that the air is moving, and we see this blurry effect. So I told you that we can see that we have air here, but sometimes we can. In buildings, we don't see that. It's very unlikely that inside, and if you see something like this inside buildings, probably because you are drunk or something like that. But when the temperature is very high and the air temperature is lower, then we see all these movements, and this is because the air layer that we have here, it's moving. Okay. But anyway, we see this effect, and that's the effect of this element, the heat, radiation, and convection coefficient. And we need a value. Okay, so we have a table, or we can use this value, and that's it. We need to know it. And finally, we have a lot of documents. Okay, because this is not something that I'm just making up right now. We have international institutions you can rely. One of them is the ASHRAE, which stands for the American Society of Heat, Refrigeration and Air Conditioning Engineers. Okay, so those guys are engineers. And then we have the ISO, which is the International Organization for Standardization. Okay, so all these values come from these two. There are other institutions, but the ISO is international and the ASHRAE it's American. So, and those are certifications. If we read this document, we can take for granted that those values or those documents are true. Okay, so don't look up on the internet. Can we find thermal conductivity of a brick? Can we find this on the internet? It's reported to be a percent of 1 plus or minus 0.4. So it can be from 0.6 to 1.4. This is the thermal conductivity of bricks. Sometimes to save time, we can rely on the internet or whatever. If you want to know exactly the thermal conductivity, or if you want to know the official thermal conductivity for things, then here we have the brick. It depends on okay, this is the unit, watt, Celsius, and meter. So what was here? Yeah, so this is international units. So it's from 0.6 to 1.4. In this table, we have 0.7, makes sense. But there are different kinds of brick. We have this brick, it's 0.72. This brick is 1.3, okay? But not all the bricks are the same. So again, don't worry, it doesn't affect too much. What we need to understand is the big number. Look at this. Okay, so here we have, and we are looking at this column, which is the international unit. Let's look at this column, the imperial units. Look at this value. This is 0.6 and this is 12. So this is a huge difference. Between 12 and 0.6, there's a huge difference. Here we have 9. Between 9 and 12 doesn't make any difference. Between 5 and 9 doesn't make any difference. Between 0.75 and 0.26 or 0.8, it's the order of magnitude. The order of magnitude is okay. We're talking about a point something or 1 point something or 10 point something. Every time we increase 1 0, then it matters. Between 7 and 8, there is no difference. But between 8 and 80, there is a difference. There's a huge difference. Okay, so this is what you have to understand. Look at solid materials, brick and concrete blocks. So brick can be from 5 to 9, and concrete can be 12. Okay, so those are solid materials from 5 to 10, right? 5 to 12. We can think that those two materials are in the same category. But if we look at other kind of materials, for example, the wood it's 0.8. Okay, because wood, it's an insulating material. So a brick, in terms of thermal resistance, it's worse than wood. And if we look at thermal insulating materials, this value would be 0.0 something. Okay, so every time we add thermal insulating properties, we move with 0 up or down. Okay, brick materials that are not thermal insulating materials, they are above 1. Good materials in terms of thermal insulation are between 0.5 and 1. And then materials that are really thermal insulating materials are 0.0 something. And this is what matters. So I don't mind if I use brick with a thermal conductivity of 5 or concrete with thermal conductivity of 10. Okay, that's fine. But then I need to add something with the thermal conductivity of 0.0 something. It's not, oh, wood is thermal insulation. Yeah, but it's thermal insulation. It's 0.8, so that means that you need probably 10 times as much wood as this to get the same thermal resistance. So if you have a 1 inch of this material and 10 inches of wood, you have the same thermal resistance. But usually we have 1 inch of wood and 10 inches of thermal insulating material. Anyway, you have these elements, so we have the thermal conductivity. But look at the units. Those units are BTU, inch, and then we have hour, so it's BTU hour, this is the power, and then we have Fahrenheit and feet square for the thermal conductivity. We have inch and feet square. What were the units that we were? Oh, I believe. Okay, the units, remember, the thermal resistance, it's hour divided by feet square, Fahrenheit, and BTU. And in this construction materials, we have BTU, inch, hour, feet, Fahrenheit, and square feet. Okay, so we have these inches here. Okay, I will explain this right now, but be careful with units. Sometimes you will find that we have BTU, hour, Fahrenheit, and feet, or sometimes you will find BTU, inch, hour, Fahrenheit, and feet square. So both magnitudes are thermal conductivity, in this case is K, but the units can be different. So it's not that we have imperial international units, is that in imperial units, sometimes you will find two different units. We have to be careful with that, okay? But in this case, we have to abide by the units that we have here. And this is what we're going to do in the next exercise. And here we have thermal resistance of cavities, of air spaces. Because if we have an air cavity inside the wall, and sometimes we have air cavities, and in glass, we have air cavities. If you look at this glass, this is triple glazing. So that means that we have 3 glass panes and 2 air cavities. Very good one, by the way. We need a thermal resistance for that air cavity. So here we have air cavities, horizontal, vertical, and here we have the width of the cavities in inches or millimeters. Well, that's complicated, so we will use this. So as we are using these tables, I will keep explaining things because the reflective surfaces affect this. Okay, so there are a lot of things involved in that. Today, we're going to keep it simple, and we're going to do something very, very basic, just to understand the what we are doing. Okay, so this is the theory. We know that the heat goes through walls. We know what we have to do to prevent this from happening, or at least to decrease the rate at which we're losing heat. And what's next? Now we have to we have to do an exercise to apply this knowledge. And this is what we're going to do now. And this is what you will be doing on your own from now until Thursday. We're going to use Excel, and you have to try to do on your own the same thing I'm doing here, and then try to work with different examples, changing the numbers, and we will end up calculating what do we have to calculate. At the end, we have to calculate the R value, and finally the U value. So what do we need? We're going to need materials here. Here we can have brick, thermal insulation, and plywood. Okay, so that would be the basic wall. We have brick outdoors, then we have thermal insulation indoors, and we have plywood where thermal insulation in the wall, and then plywood indoors. So we have materials, and what are the parameters that we need here? So the first thing we need is the thermal conductivity. If it's we can change the width of the cells, or we can click here and wrap text and try to make it nicer. Conduct T. There you go. Okay, so we have material, thermal conductivity. What else do we need? We need thickness. Okay, so we're preparing our table, and then we have to calculate the R value, and then we have to calculate the U value. Is this enough, or do we need something else? Well, in materials, we have brick, we have thermal insulation, we have plywood, but first we need to, I'm going to insert a couple of rows here, and I want this to be exterior because the order is important, and this has to be the interior. Okay, so before everything, we have air, exterior, and here we have air, interior. Okay, so at least I told you that we need 5 layers, 1, 2, 3, 4, and 5 layers. And then we have thermal conductivity, we have thickness, and for the air, we don't have thermal conductivity or thickness. We have this H value, which is the coefficient for convection and radiation. Okay, thermal conductivity, thickness, and H. I want you to include the units. Okay, so the units are important. What are the units of thickness? We're going to use inches. Okay. What are the units of thermal conductivity? So that's why if you're using the tables that we have on this PowerPoint, okay, so what are the units here? It's BTU, inch, hour, Fahrenheit, feet square. So what are the units of thermal conductivity? It's BTU divided by hour, no, BTU, inch, divided by hour, Fahrenheit, and feet square. Those are the units of the thermal conductivity. If you want to make it nicer, you have to press Alt and then Enter, and you have a different line. It looks better. Okay, so we have thermal conductivity, we have inches for the thickness. What are the units for H? Let's find out. The units of H were here. BTU, hour, feet square, Fahrenheit. So the H is BTU divided by hour, Fahrenheit, and feet square. Make it a little bigger. Okay, so those are the columns that we need. We need the material, we need the thermal conductivity of the material, we need the thickness of that material, and for the air layer, we are going to use the H coefficient. So we don't have thermal conductivity when we have air, and we don't have H when we have solid materials. Okay, but we need all these. And finally, we need the R value. And what's the R value? In this case, the R value of the external air, I can click here, equal 1 divided by this. It's an error or a warning here because we don't have any values. Because what's the thermal resistance it was here. Yeah, the thermal resistance of the air layer is 1 divided by H. Okay, and the thermal resistance of solid materials is the other way around. This is the conductance. The thermal resistance is 1 divided by this. I use these two values because we can work with either of them, C or R. We're using R, so this is W divided by lambda. So thickness divided by the thermal conductivity. So for this one, that equals the thickness divided by the thermal conductivity. And here we have another thing like that. We can drag this until the plywood, and here that equals 1 divided by this H value here. Okay, I think we need to run some numbers to see if we are doing things correctly. So let's look at the table. First, we need brick. So we have to go down, and here this is cavity gypsum. Okay, here we have brick. Which one do we use? This brick common or brick face? What do you think? Any of them? Okay, so that's a question that you usually. Is it brick? Is it concrete with whatever related, or is it gas insulated? I told you that if we are in the same order of magnitude, it doesn't matter that much. Okay, so we are using either 5 or 9. Let's use 5 for this exercise. So for the brick, the thermal conductivity is 5. The thickness matters, especially because there, for example, when it comes to the thermal insulation, I can decide the thickness. For bricks or concrete walls, I cannot say, okay, I want 7.5 inches or 2 feet and 3/4 of an inch. Bricks, usually they are manufactured and they are the same all over the world. I don't know why there is not an imperial layer or an imperial brick or international brick. There are no differences that I know of. Well, there's a special region in Spain in which they have a special brick because they are a bit crazy. But what's the dimensions of brick? Standard size of brick in millimeters or standard size of brick in inches. So the brick can be either in the long, so we have to, it's a rectangle, so we can have either 3.54 inches or 7.48 inches, kind of, okay? So there shouldn't be a difference between, so if we are placing the thickness, well, it depends. If we have this layout, this is the thickness, and if we have the other layout, this other thickness. We're going to use 3.5, okay? So we're going to use 3.5 inches. So this, if we click here, you can see that it's D6 divided by C6. Okay, so if you double click here, you see the columns or the cells that are involved in this formula, so it works. What about the thermal insulation? So let's go to this. This is the plywood, gypsum, sheeting materials, construction materials, air cavities. Where do we have thermal insulating material? Okay, this is this table 2.4. We have well, they consider OSB plywood as almost thermal insulation material, but this is what really thermal insulating materials look like. Okay, so it's a 0.1. I told you 0.0 something. Well, it's 0.1, 0.2. So this is the extruded polystyrene, the fiberglass, fiberboard, polyisocyanated insulating board, whatever. Anyway, that matters because we have to select the one with the lowest thermal conductivity. So the extruded polystyrene is the best. And the fiberglass is not as good as this one. And fiberboard, this is fiberboard. It's wood. Okay, so there's not a big difference between this one and that one. Probably the thermal conductivity of this is a little lower, but between the plywood, which is okay, sorry, we have to look at this. Okay, so there's a difference. We have to look at this column. So the OSB, it's 0.8, the fiberboard is 0.3. Okay, there's a difference. And we don't have information about this. Well, you will find this many times. Okay, if you look at the extruded polystyrene, we don't have information about the thermal conductivity. We do have information about the thermal resistance. Why? Because if you look at this, we have the thickness here. Okay, so we have a board, and this board is 1 inch or 25 millimeters. Is this 1 inch? Kind of. So imagine that this is 1 inch of this material. So that board, we don't have the thermal conductivity. We have a thermal resistance. So the thermal resistance is 1 inch, 5. So if 1 inch has a 5 thermal resistance, 2 inches. What is it? 3 inches, 15, 4 inches, 20. You get the point? So can we understand the thermal conductivity of this extruded polystyrene? If the thickness is 1 inch, and then the thermal resistance is 5 what? Our Fahrenheit feet square BTU. Our Fahrenheit feet square divided by the BTU. Thermal resistance is thickness divided by the thermal conductivity. So if we want to find the thermal conductivity, this equals thickness divided by R. Okay, so if this is 1 inch, and this is 5 our Fahrenheit feet square divided by BTU. Are these units at the end? It's at the end, it's a BTU inch divided by our Fahrenheit feet square. That are the same units we have here. BTU inch hour Fahrenheit feet square. Okay, so 1 divided by 5, it's 0.2 BTU inch hour Fahrenheit feet square. Okay, so what is the thermal conductivity of extruded polystyrene? It's 0.2. And now we can select here the inches, let's say 10. Don't save money on this. And finally, we have plywood. So let's look at this. Okay, so this is sometimes when we don't have the thermal conductivity in this column, then we have to do this. We have to select the thermal resistance, and here we have information about the thickness. Okay, so we have to divide the thickness divided by the thermal resistance, and we get the thermal conductivity. And so now we have to go to plywood. We have plywood here, and the plywood we do have this is 0.8. So the plywood thermal conductivity is 0.8, and the thickness, let's say, how much is this? Half inch. Half inch. And here we have this. Okay, so we are done with the solid materials. Now we have to do something with the air, the internal and the external air. So we need to go to another table. We have this one. And we have interior and exterior. We need different tables for this. So once we have this one, okay, that's great because this works for walls. Then if we want a different table for roofs, I can select all these, right click, copy, right click, insert copied cells, and now I can have this for roofs. And I can do the same thing for floors. Okay, so once we are done with this, but I have to change the age because the age for walls and roofs is different. So let's do it with walls. So for walls, it's this. Interior is 1.6, exterior 2.93. So interior is 1.6 and exterior 2.93. And this double click, it's 1 divided by this, and this one is 1 divided by this. We are architects, and the 7th decimal doesn't matter. Even the 3rd decimal doesn't matter. Is how can we do it? If we, because this is a non-professional Excel file, but if we right click here and we select format, here in number, we can select the decimal places. 2 is enough. So we select this decimal place, and then if we click here, this paintbrush, format painter, and we select all the cells with the same format, that's fine. So we have 2 decimals everywhere. So in fact, I'm going to do this. I'm going to select this and all these cells. I want the same format with 2 decimals, and this one, these cells too. Okay, what about for roof? For a roof, if it's winter, the heat goes up, and this is 1.6, 1.96 and 2.93. So the interior is 1.96 and the exterior is 2.93. Okay, so I have created an Excel file, and now I can, if I want to change the thickness, okay, what if I have only 8 inches of thermal insulation? So these are the thermal resistances of this. Okay, so now by changing the thermal conductivity or the thickness, I can change the thermal resistance easily. I don't have to do it thousands of times. What is the total thermal resistance? If I want to calculate the total thermal resistance here, what do I have to do? I have to select this cell And now I can apply this. I insert function, and the sum is the first. I click OK. And if you select all the cells that you want to add up, and click OK, here you have the total thermal resistance. You click here, double click, and these are all the cells that we're adding up. Okay. Finally, what is the U value? The U value equals 1 divided by this value. And there you go. And I want 2 decimals. This is it. Units. We don't have the units here. It's BTU, hour, Fahrenheit, feet square, and the units of the thermal transmittance is just the other way around. No, sorry, I made a mistake here. And here it's BTU divided by hour Fahrenheit square. So once we have this, now if I change, if I don't want brick, I want a concrete block. So when it comes to concrete blocks, I can come here, and here we have concrete blocks. We don't have information. Okay, so you see that here, the concrete block, I don't have the thermal conductivity. I have the thickness and the thermal resistance. So I should do the same. So I'm going to use concrete cast in place. Okay, so the concrete has a 12.5. So if this is not a concrete block, it's just concrete cast in place. This is 12.5. And then everything changes here. The important thing here, look at this. I can change the thickness of the concrete. I have 3, I can have 5. Look at the total thermal resistance. If I double the thickness of concrete, it changes from 41 to 42. If I double the thermal insulation, it changes from 42 to 82. Okay, so that's why if I want to increase the R value, what really matters is the thermal insulation. So if this is 12 or 10, it doesn't matter, it's 82. Okay, so that's why don't go crazy with if it's 10, if it's not 10, if it's 11, it's still 82. But if what really matters is changing the thickness of the thermal insulation. This is what really matters. The plywood, what if I, instead of ½ inch, I have 1 inch from 52 to 53? Doesn't matter at all. Okay, so this is the I want you to do this. Okay, so I just want you to create that Excel file, and then you have to submit an Excel file with at least 4 walls and roofs. And if you want to add a different material, imagine that here we insert, okay, and if we want to add up everything, we include this gap here. Imagine that we have an air cavity. This is an air cavity. And do we have information here about air cavities? We do. Here we have air cavities. First, it's for cold or for winter, for summer. If we're in winter, we are here. Is it a wall? If it's a wall, it's a vertical air cavity, and the direction of the heat flow is this. And so if we have this, the cavity, well, we have the thermal resistance and all that with the non-reflective and reflective surfaces. Okay, let's select this one. But anyway, that thermal resistance of this cavity would be in vertical, let's say 1.1, 1.02, 1.01, let's say 1.01. And this, if it's an air cavity, this has to be 1 divided by this. There you go. But again, does it affect too much? Not really. What really matters is the thickness of the thermal insulation. This is what really matters. Then we can make it nicer. I don't know if you can work with Excel. We can always merge. We can center things. We can use different colors. If you want to make sure that this is an air layer and it's something different, you can do something like this to make sure that when you are in this row, you have to do something different. And if you want to highlight the results, use something like that. Use your creativity to something, but the most important thing is that the Excel file, it has to work. If it's nice, be great.